All right, how's it going? Welcome back to another video here in the series on mechanics and relativity. You might have noticed that the section title has changed. We are now onto a new section here called Central Forces. And personally, I'm excited to be getting into this new section, but really at this point in the video series, I guess in general, because at this point in the video series, we're almost sort of at a transition point, going from the first sort of overall third of material in the video series, which has been kind of sort of the foundations. And that's what we've been doing the last three sections, right? Where in the first section, we talked about Newton's laws, point particles, inertial reference frames, all of that stuff. Then in the second section, we talked a lot about forces, talked about how they can get defined in terms of potentials, specific types of forces, and how we can incorporate different forces into Newton's laws. And then most recently in the last video, we spent just a little bit of time talking about dimensional analysis, right? Where we say that physical quantities have dimensions associated with them. It's important that we get them right, but also we want to think of them as tools to help us solve problems too. They can be our friend rather than this thing that we have to just carry along with us. But anyways, all of that is to say that those first three sections were kind of just talking about the foundations of physics. What are some of the underlying most basic principles, at least when it comes to mechanics, right? And then that's usually people's starting point. But what that means though is assuming that we have a good grasp of the basics of mechanics. Now we can start to dive into more detailed topics, saying with the foundation that we have, how can we use that to build our knowledge of physics? And it's at this point where we're going to start getting into more, like what we said, more detailed and maybe it's biased, but I think more interesting topics is naturally going to come with the idea of having more details to sort of learn about, right? And then the first sort of more detailed section, if you want to call it that, is this section here on central forces. Now, we have introduced central forces at some point in one of the videos in this video series, but what we're going to do is we're going to kind of just reintroduce it, but now kind of sort of lay it out as the main character and what we're trying to understand here. This is the main thing that we're going to be focusing on. Okay. And the real goal here is not just to reintroduce the idea of a central force, because we might already remember what that is, but if not, that's okay. But also, what I want to get across is what can we learn about a specific problem when we see that a particle is under the influence of a central force and how it's different from any generalized force. Okay. It turns out there's a lot that we can say, and there's a lot of sort of simplifications to a problem if the force that we're working with is a central force. So just understanding that is going to be kind of the main goal of this video. I realize as I'm saying that might feel a bit vague, and I'm literal hand waving. I'm waving my hands as I'm saying it, right? But we're going to see what I mean as we go through this. So to start off, I'm going to just write out, I guess, Newton's law in the general case over here, what Newton's law looks like if we're working with a central force over here, and then we're going to kind of start the discussion on central forces at that point. Okay, so I have writing on both sides of me here, where on this left-hand side of me, we have Newton's second law written out in the general sense. And on the right-hand side, we have something that I'm calling central force motion, which is, this equation here is just Newton's second law if the force that's acting on a particle is a central force as opposed to a general force. Okay. Now, really quickly, I just want to go back and sort of review Newton's second law just for a moment, just to highlight what would be needed in order to solve the equations of motion. Okay. So this is kind of a more mathematical version of writing F equals ma. Of course, there's no actual F here. There's no explicit force, and that's because we're defining our force in terms of the gradient of a potential. again, it's the gradient because we're working in 3 spatial dimensions. So our potential depends on a vector x, or x comma y comma z, if we want to think of it that way. And on the left-hand side, right, we just have m as the second derivative of a vector x, so x comma y comma z. And the important things that I want us to keep in mind here are, one, that this is a second-order differential equation, because we've got 2 dots on the x, right, on top of x. And then also, it is a vector differential equation, right? The potential depends on a vector input, x, and then the acceleration is itself a vector. And assuming that we're working in 3 spatial dimensions, that means that if we wanted to solve a problem that involved solving this sort of differential equation right here, what we're really doing is we're solving a set of 3 different second-order differential equations. And I say 3, meaning 1 for each component of the vector x. Or we could say it's a vector second-order differential equation, right? So that's the basic idea with the general case of Newton's second law. But it turns out that when we're working, if we're working with a central force, we're going to, again, just describe what that means in case we forgot. But we're going to see that the amount of work that is needed to solve the central force problem is actually kind of reduced compared to the amount of work that would be needed to solve this differential equation, sort of in the general case. But before we get into how we can reduce the problem or simplify the problem, let's just quickly review what a central force is, right? And we're going to see that both equations here, it's Newton's second law, and they're both similar, but the main thing that's different between them is the input of the potential function, right? Over here, the potential function just depended on any set of input spatial coordinates, whereas here, v now depends not on an input vector, but on a scalar quantity r, where r is just the magnitude of our position vector, okay? So what this is saying then is that we have a potential that only depends on a radial distance, and then in turn, that means the force that's defined from this potential also only depends on this radial distance right here. That means F would be a function of r. Forces that only depend on a particle's radial distance from the center is known as a central force, okay? And that's kind of what distinguishes a central force from a general force. So hopefully that sounds either familiar or hopefully it makes sense. And what we're going to do to start this discussion here is to say, well, yeah, how exactly can, just by changing the input of this scalar potential function right here, changing it from a vector x to the magnitude of the vector x, right? R is just the magnitude of the vector x. How does that simplify the overall problem? And we're going to take our first step here. The first step is going to be looking at just the quantity of the angular momentum associated with a particle, right? And hopefully we remember this. The angular momentum is denoted as the letter L, and it's defined as the radial distance in a cross product with the linear momentum, right? So this is angular momentum, this is linear momentum. And what I'm going to do now, this is often how it's written, but to keep the notation sort of consistent, because I have x's right here, and to not confuse this vector r with the magnitude distance r, I should really be writing this as the vector x, right? I realize this is like x and then the cross product looks like x too, right? But this is position vector cross linear momentum right here. That's what we have. So this is just the general angular momentum of a particle. And what we can do is we can rewrite this, because the linear momentum is just m times v, the mass times velocity of the particle. I can bring the mass of the particle out to the front, and then let's see what we have left over within the cross product. So we still have our position vector and a cross product with the velocity, which we can just write it as x dot, right? So that's how we can rewrite the angular momentum. Again, we can bring the m out front. M really belongs right here, but we're bringing it out to the front because it's a constant. The mass of the particle we're assuming is not changing with time. And what is interesting about the angular momentum when working with a central force problem, and we mentioned this at one point, but we're going to go through it again, is that the angular momentum associated with a particle under the influence of a central force, its angular momentum is conserved. And that's going to be the first thing that we show. So let's do that, okay? Let's show that this quantity right here, the angular momentum of a particle, is conserved if that particle is under the influence of a central force. Now, we typically show that something is conserved by just taking the time derivative of that quantity and setting it to 0. Or in showing that it equals 0, I should say, right? So let's do this. Let's take the time derivative of this quantity. Taking the time derivative of this is going to give us two terms. The first term comes from differentiating the first input to the cross product. So that's going to be m times x dot cross x dot. I hope that x's aren't too confusing. I hope we distinguish what I'm saying here. But this is differentiating the first term, or the first input in the cross product, keeping the second one fixed. And then we have the second term, right, from product rule, which keeps the first term fixed and differentiates the second one right here. So then we have x times x double dot, x cross x double dot. Okay. So hopefully that makes sense. Now, with this first term right here, this term actually goes to 0. The reason, I guess is 0 vector, but the reason being because any vector in a cross product with itself must be 0. That leaves us with just this term right here. But now what I'm going to do is I'm going to rewrite this second term, and I'll do it in a line below here. So the first input to the cross product is x, the position vector. That's in a cross product with, and I'm now going to sort of put the factor of m back right here. So we have m times x double dot. But keeping in mind, m times x double dot, that's just the left-hand side of Newton's second law, right? So that's equal to this quantity right here. And I'm going to essentially rewrite mx double dot as the negative gradient of the central potential. So there's going to be a negative, that's why we have that factor right there. And now I'm just going to write the gradient of v of r, like this, okay? So hopefully that makes sense, just bringing m back in here and then applying the definition of Newton's second law. And now at this point, we're just going to rewrite both terms in this cross product, where the first term, this position vector right here, if we wanted to write the position vector in a given coordinate system, specifically spherical coordinates, it would have, well, let's just start maybe quickly with Cartesian coordinates, right? If we were to write the position vector in Cartesian coordinates, it would be x times I hat plus y times j hat plus z times k hat, right? That's how we'd write the position of a particle in Cartesian coordinates. But if we're working in spherical coordinates, it would be the magnitude of this vector pointing in the radial direction, okay? And hopefully we're familiar with that, or familiar with spherical coordinates, but that's how we could write our position vector in that coordinate system. So we're going to do that with this first input right here. Maybe I'll just put another equal sign, and then we have our minus sign. The position vector, which is equal to this, so r times r hat, and a cross product with the gradient of our potential function, which only depends on r, right? Now, if our potential function only depends on r, the radial coordinate, well, that first means that we should probably compute the gradient in spherical coordinates. But if our input function only depends on r, meaning it doesn't depend on the angular coordinates theta and phi, the gradient of this potential just becomes the derivative, the radial derivative of this function. So because this only depends on r, specifically the radial coordinate, we can re-express this gradient as just the radial derivative of r, and it points in the r hat direction. Okay. So hopefully that makes sense. And now at this point, we can see that we have some magnitude in times the r hat direction and a cross product with some magnitude times the r hat vector. These vectors are going to be parallel, and whenever you have two parallel or anti-parallel vectors, their cross product is going to give you 0, meaning that the overall angular momentum, the time derivative of the angular momentum goes to 0, meaning the angular momentum is conserved. So, okay, sure, angular momentum is conserved. That's one thing that we can say about a particle if it is under the influence of a central force. But what I want to do now, and the big picture idea to connect the dots here, is to say, because angular momentum is conserved, what does that mean then for the motion of a particle? Okay, and to start to understand why, maybe we'll draw something up here, but I'm just going to quickly write out two more identities. The first is that we know that L dotted with the position vector needs to give us 0, and also we know that L dotted with the velocity vector needs to give us 0. Now, why is that, right? Well, the reason is just coming from the definition of the angular momentum. The angular momentum, L, is defined as a cross product, where the cross product has inputs x and x dot. So by definition, the output of the cross product needs to be perpendicular or orthogonal to both inputs, and that's just what we're saying right here. So this comes just from the definition of the angular momentum itself. Whether angular momentum is conserved or not is irrelevant. This is always going to be true. Okay. Now, how can we use these statements right here in combination with the fact that angular momentum is conserved to tell us about the motion of a particle? So what I'm going to do here is I'm just going to draw out an arrow. It's pointing up. We're going to call this arrow our angular momentum. And if angular momentum is conserved, that means this L vector right here is fixed. It's not moving. It's not changing its magnitude, or the arrow is not moving in space. Okay. And because L is pointing directly up, let's just say that this is the z direction, for instance. Okay. Now, keeping that in mind, we have a fixed vector. What can we then say about the position of a particle if, based off of this equation and just saying that L, maybe I won't even write vector L, I'll just say that it only has a z component, right? L sub z. Well, if the position vector x is perpendicular to the angular momentum vector, and the angular momentum vector has a z component, that means no matter how I write my position vector, it needs to only have x and y components, right? It can't have a z component in order to be orthogonal to it. So maybe if I draw x like this, that means that x is going to have some x component, a y component, and then 0 for its z component, right? Now, same thing with the velocity vector, right? With the velocity vector, it is also perpendicular to the angular momentum vector. So if L is pointing in the z direction, our velocity vector, which does not, keep in mind, it does not need to be also perpendicular to x, it just needs to be perpendicular to L, so I can draw it like this, where these do not need to be right angles to each other. X dot can have components x dot, y dot, 0. Okay. So we're saying a lot, but hopefully the idea makes sense, right? That because x and x dot are perpendicular to L, this is what their components would look like in the general case. Now, just keeping in mind, if we had a particle which did not have a z component for its position or velocity, we can almost just think of that particle existing within a 2D plane, right? We know this is always going to be 0. So when a particle only has x and y components for both its position and its velocity, that means that the motion of a particle is now confined to that xy plane, okay? And that's kind of what this conservation of angular momentum is telling us for the motion of a particle. If L is conserved, and here's sort of the more general statement, if L is conserved, then the motion of a particle is going to be restricted to the two-dimensional plane perpendicular to L, right? Now L is pointing in the z direction, so in this case, the motion of the particle is restricted to the xy plane. But if we were to say that L was this vector right here, oriented at some angle, what that would tell us is that the motion of the particle would be then restricted to sort of this plane that is perpendicular to the direction that is perpendicular to the vector pointed in the direction where that's defined by L, right? Hopefully that makes sense. So that's kind of the first step, is that when working with a central force, we can reduce our three-dimensional problem. We started with a three-dimensional problem in the general case of Newton's second law. But just from the fact that we have conservation of angular momentum, we can now say that our particle moves within a two-dimensional plane. Okay. Now it turns out that's not all that we can do. We can simplify the problem even further than that. In order to do that, though, we're going to need to erase the board and start fresh. So I'm going to do that, and we're going to continue from there. Okay, so this is what we have so far, right? We have an equation of motion for a particle of mass m under the influence of a central force. And we just showed, right, that angular momentum is conserved, which means conceptually that the particle, whatever that particle is that's influenced by a central force, it is going to have its motion restricted to a plane, where the plane is going to be perpendicular to the direction that of the angular momentum vector L itself. Now the question though is, well, can we simplify this even further, right? We've already said the particle is restricted to a plane. Can it be restricted even more? And in some sense the answer is yes. In order to see how that happens, how can we talk about restricting quote unquote the particle's motion even more? What we're going to need to do is we're going to need to write out both sides of Newton's second law here in terms of its components. Now, in the general case, we might think of I hat, J hat, and K hat components, but we already know from conservation of angular momentum that the particle is going to be restricted to the motion of a plane, right? So ideally, we can express both sides of this equation right here in terms of a set of two-dimensional coordinates, because it's motion in a plane, right? And furthermore, because a central force only depends on the radial coordinate, one common coordinate choice for motion in a plane, where one coordinate is the radial coordinate, is to say, well, let the other coordinate be the angular coordinate and work in polar coordinates, right? So that's what we're going to do. What we're going to do kind of as this next step is we're going to say, let's write out both sides of Newton's second law here in terms of polar coordinates and say, what can we use with those components to tell us about the motion of this particle here. Now, in order to do that, that's going to require, and most of the work is going to require, taking the second time derivative of the position vector. Now, for the right-hand side, of course, we're just taking the negative gradient of the potential function, but we've already seen, at least in the previous whiteboard, that this is simply negative dv dr, just the r derivative of the potential in the r hat direction, right? So we already have the polar coordinate components for the right-hand side. It doesn't have any theta hat component. But what we're going to try to do is say, how can we write out this left-hand side in terms of polar coordinates? So starting with the position vector, we've described how that is just the radial coordinate in the r hat direction, right? Now, to obtain the velocity of a particle in polar coordinates, we might initially think that we can just say, okay, well, that's the time derivative, right? And we just take the time derivative of this thing. Take r dot, and that exists in the r hat direction. So is that not just the velocity in polar coordinates? And the answer is, well, that's part of the velocity, but that's not all of the velocity. And to understand why, we need to go back to a fact regarding just polar coordinate basis vectors in the first place. And I'll try to be quick with this because I'm assuming that we've heard of this before, but I want to just go through it again in case we need a refresher on it. So let's say that we have just a particle that's moving in a circle, this circle right here. And it maybe starts at this point and then it moves up to maybe this point over here. If we wanted to define basis vectors at both of these points, let's start with Cartesian basis vectors, the I hat and j hat basis vectors. We can ask ourselves, where do I hat and j hat point at each of these positions on the circle? Well, I hat and j hat would look like this and this, right, at this initial point. And then as we move up to this upper point on the circle here, I hat and j hat are still going to have their same shape. I hat and j hat are still going to have length 1, where I hat points 1 unit in the positive x direction, j hat points 1 unit in the positive y hat, or y direction. Might have misspoke there, but you get what I'm saying, right? The idea is that they're going to remain fixed as the particle moves along the circle. Now, what about polar coordinates, right? Let me erase these I hat, j hats that we have here. If this is our starting point on the circle, in polar coordinates, in r hat and theta hat basis vectors, the r hat vector is going to point radially outwards, right? So that would be r hat, and theta hat's going to point on the direction perpendicular to it. So theta hat would look like that, right? Now, what about as we traverse from here up to this upper point? Now r hat is still going to point radially outwards from the circle, and theta hat is still going to be perpendicular to r hat. But the idea that I want to get across is that as our angle changes, and as time changes from this starting point to this ending point over here, notice that the r hat vector has physically changed. The r hat vector is not constant. It started like this, and now it's like this. Same thing with theta hat. It starts pointing here, and now its direction is literally shifting. So the big picture idea here is that r hat and theta hat vectors are not constant in time. So when we take the time derivative of this expression right here, not only does the magnitude of this vector change, which is what we accounted for, but also the direction itself changes. So this is really a product rule, and this is just the first term within the product rule. So let's compute the second. The second term in product rule gives us r times the derivative of the r hat basis vector, right? Now, what we can do is we can re-express this, we can rewrite this, so it's not dr hat dt. Let's just first write out the same first term. We have r dot times r hat plus r times, and then I'm going to rewrite this using chain rule. So not dr dt, but rather dr hat d theta dt, like this. And now, just as one final step, we can say that this first term is still the same. We have r dot times r hat plus r. I'm going to look at this term next. D theta dt is just theta dot, like that. And then finally, we have the derivative of the basis vector with respect to theta. Dr d theta hat is just, dr hat d theta is just theta hat. This is just a property of polar coordinate basis vectors. So this expression right here, the sum of these two terms, would be the velocity of a particle in polar coordinates. It's both a radial and angular component. Now we're just going to do the same thing in computing the second derivative, because that's what we really need to do, right? So let's look at now x dot here. If you haven't done this before too, this might be a good point to see if we understood the logic here, to go through saying, well, try computing the time derivative of this overall expression and seeing if you get the same thing that we get here on the whiteboard, okay? Now, taking the time derivative is just going one term at a time. We're going to start with the time derivative of this thing right here, which itself is a product of two time-dependent quantities. So we need to apply product rule here. First term in the derivative is just r double dot times keeping r hat fixed. And then the second one is going to be r dot times the time derivative of r hat. Well, we said that the time derivative of r hat right here is just theta dot times theta hat. So I'm just going to write that right here. So this is just theta dot times theta hat for the same logic that we applied up until this point. That would be the time derivative of the first term. Then we have the time derivative of the second term, where we take product rule once again. We start by differentiating the first term, giving us r dot theta hat. Differentiating the first, keeping the rest fixed. Then we're going to differentiate the middle term, keeping the rest fixed. So this is going to be r times theta double dot theta hat, like this. And then finally, we're going to keep the first two terms fixed. So r theta dot theta hat, the time derivative of that, right? So we're going to have d theta hat dt. Okay. Now we're going to apply a similar trick, or a similar sort of just application of chain rule that we did right here when computing dr hat dt. Turns out d theta hat dt can be expressed as d theta hat d theta dt. Okay. So this term right here, we're going to have, well, maybe let's just say, what are both of these two terms, right? So this term, d theta hat d theta, gives us negative r hat. That's just, again, a property of differentiating polar basis vectors. And then d theta dt gives us another factor of theta dot. So keeping in mind that negative theta dot times r hat, that's what this time derivative is right here. So let's just plug this into here. So we already have a factor of r. Well, we have a minus sign first, right? So we have a minus sign, we have a factor of r. We have one factor of theta dot here. And then we have another factor here. So we have theta dot squared. And that points in the r hat direction. Excuse me. So kind of a lot of steps, right? But again, this is just applying time derivatives to polar coordinates and their associated basis vectors. And this is what we get. So now what we're going to want to do before sort of proceeding to the next and sort of the final couple of steps before we call it at this video, what we want to do now is we want to say, all right, this x double dot, when multiplied by a scalar, the mass m, this is the left-hand side of Newton's second law, where this is the right-hand side. So what we can do now is we can group terms together. Specifically, let's do this in two separate steps. We're going to start with just grouping the r hat and theta hat terms together for the acceleration vector. So when we do this, we're going to first group the r hat terms together. Out of the 1, 2, 3, 4, 5 terms, see, it looks like this has an r hat, this has an r hat. So let's collect those together. Doing that's going to give us r double dot, and then minus r theta dot squared r hat. All right. Those are the two terms for the acceleration vector that have r hat. Now for the theta hat terms, we have 3 terms here, but these 2 terms are the same thing, right? We have r dot theta hat plus r dot theta hat. So this is going to be, it's got a little flow to it, right? So we can add these 2 terms together to give us 2 times r dot theta dot. And then we also have this term right here, which is plus r times theta double dot theta hat. So this is what we get when we collect terms for the acceleration vector. Now what we want to do, and I'm glad we kind of did this in 2 steps, is now what we want to take the r hat and theta hat components of the left-hand side and equate them with the r hat theta hat components of the right-hand side. That's going to give us 2 equations, and we're going to be able to use those equations to kind of tell us more about the motion of a particle under the influence of a central force. Okay. So let's start with, we're going to need to write out 2 equations. Let's start with the r hat equation. On the left-hand side, we have mass times the r hat component of the acceleration. That's this thing right here. So one of our equations is going to be mass times this thing right here in parentheses, which is r double dot minus r theta dot squared. That's the left-hand side of Newton's second law. The right-hand side is just the negative derivative of the potential. So this is going to be equal to negative dv dr. And this is one equation. Okay. Now we're going to do the same thing with the theta hat components. On the left-hand side, we have mass times the theta hat component of the acceleration. So this is going to be m times 2r dot theta dot plus r theta double dot, like that. And then what's the theta hat component on the right-hand side? Well, there is none, right? This is just there's just this derivative right here. So the right-hand side for the theta hat component would just be 0. So we have these two equations right here to describe the motion of a particle under the influence of a central force. And we're going to start to kind of manipulate and work with these equations to simplify the problem even further. Okay. Of course, we're out of room though, so I'm going to erase what we have here, write these equations at the top, and then proceed from there. Okay, so this is kind of the summary of what we have so far. We said that for a motion that is under for a particle, that's under the influence of a central force, its angular momentum is going to be conserved. And then if we were to write out the corresponding equations of motion, this would be the radial equation of motion right here, and this would be the angular equation of motion. I was originally thinking I'm just going to fit the remainder of everything into one whiteboard, but it feels like it might be a little bit cramped if I were to do that. So I think I want to just go one of these equations at a time, and then we'll sort of connect all the dots by the end of the video. So I want to start with this theta hat component right here, or the theta hat equation of motion, because what we're going to see is that we're going to use the results of this equation and sort of substitute them into here to make some important statements. So let's just start by writing out this equation out here, where we have m times, 2r dot theta dot plus r times theta double dot equals 0. All right. Now, the first thing that we can do is we can just divide the mass out of the particle's mass over to the other side, or divide it out. And the reason, right, is because we're assuming that the particle that we're working with has mass. We're assuming this is not a photon, so the m is just going to be some positive number. You can divide a positive number over to the other side. And that leaves us with this right here. Now, to simplify this further, there's a way that you can rewrite this left-hand side. And without trying to sort of motivate it, I think I'm just going to do it. Excuse me. I'm just going to write it out, and then we'll see why it makes sense. But it turns out that this expression right here can be rewritten as 1 over r times the time derivative of this quantity r squared theta dot right here. Okay. So kind of weird, right? But to see why this is equal to this, I think it's just a matter of applying the time derivative to this product. First thing in the product would be taking the time derivative of r squared. That gives us a factor of, here, let's just literally do it. We have 1 over r, and then time derivative of the first thing is going to be 2 times r, then times r dot, right, from chain rule. That's the derivative of r squared, and then we have theta dot, plus we're going to keep r squared fixed, and then take the time derivative of theta dot, which is theta double dot. Should not be 1 over 2, 1 over r, right? And then the factor of r here cancels with the factor of r here, and one factor here, leaving us with 2 r dot theta dot plus r theta double dot, like that. So how somebody saw that or recognized that off the top of their head, I don't know, but good for them. But this is an important thing, to be able to rewrite this left-hand side this way. We still have 0 on the right-hand side. Because now what we can do is we can do something similar to what we did with the mass, we can just sort of multiply the radius to the right-hand side. We're assuming that the particle is some distance r away, so r has to be a positive number. So we can multiply that out, and that leaves us with the time derivative of something equals 0. This is the condition to show that this quantity right here is in fact conserved. So by doing some sort of fancy, not fancy, but just some very clever rewriting of this left-hand side, we've now found another conserved quantity, just like angular momentum. But it turns out that this is not some new magical angular, or I should say, this is not some new magical conserved quantity. R squared theta dot is actually related to the angular momentum itself. What I'm going to do right now is I'm going to call this conserved quantity, I'm just going to give this a name. I'm going to say that this new quantity, r squared theta dot, I'm going to call it L, lowercase l, or I guess script L, or whatever you want to call it. But I want to show how little l is related to the angular momentum, big L. And to see how it's related, let me just write out angular momentum again down here. If we remember, angular momentum is m times x cross x dot. And to see how this conserved quantity, little l, let's do this, little l is equal to this. To see how this conserved quantity is related to the angular momentum, I'm just going to write out the components of x and x dot in terms of their in terms of their r hat and theta hat, their polar coordinate components. Words seem to be tough for me today. I'm not sure why. But if we were to rewrite this, we would get m times the position vector, which is just r times r hat, in a cross product with the velocity in polar coordinates, which if I remember, that's r dot r hat plus be r theta dot theta hat, right? We computed this in the previous whiteboard, the velocity of a particle in polar coordinates. Now, this is a cross product between, I guess the cross product can be distributed into this cross this plus this cross this. Now, r hat crossed with r hat, regardless of what the magnitudes are, that goes to 0. So this doesn't contribute to the cross product. And what we're left over with is we have this factor of m. Then we have, I'm going to bring all the coefficients out front and just leave the basis vectors to the end. So we have m, we have a factor of r here. We have another factor of r, making this r squared. And we have a factor of theta dot, like this. And then we have r hat cross theta hat. R hat cross theta hat, like this. So this is how we can write out, this is another way of writing out the angular momentum vector. Now notice that L is m times r squared, pointing in some direction. Or I should say m times r squared theta dot, pointing in some direction. Whereas this lowercase l is just r squared times theta dot. So what we can do then is we can say if we were to excuse me, if we were to take the magnitude of L, I apologize to you, I've been sick the past couple of days. I've been trying to get over a cough. But if we were to take the magnitude of L, that would just be this quantity without the vector components, right? The scalar quantities out front. So the magnitude of L is just going to be m times r squared times theta dot, but we said that lowercase l is r squared times theta dot. So the magnitude of the angular momentum vector can also be written as just m times just lowercase l right here. So they're connected somehow, right? What is this actually telling us in words? Well, what we found at the beginning of all this is that angular momentum for a particle is conserved if it was influenced by a central force, right? What we're finding now here, is that there's some new conserved quantity, r squared theta dot, which we're calling little l. And then finally down here, we're saying little l is related to the magnitude of big L through this equation. What this is telling us is that this new, excuse me, this new quantity, little l, is just the magnitude of the angular momentum vector per unit mass, okay? So really, it looks like we found some new conserved quantity, but it's really just a scaled version of the previously conserved quantity that we found. And that might initially sound disappointing because it might seem like, oh, well, we don't have any new information then. We're basically just rediscovering this. And it's great that this is conserved, but we already did that, right? Well, it's going to turn out that this is going to be useful still to be able to write this combination of r squared times theta dot as just some constant L. After all, this thing is a constant value, right? Its time derivative does go to 0. So by incorporating this constant L here, we'll be able to use that in this equation, and we'll be able to sort of finish the discussion by writing out the radial equation of motion using this angular momentum per unit mass. So I'm going to erase the board and then we're going to do that to finish up the video. Okay, so to finish out the video, and I think this will be kind of cool here, we're going to connect some dots together and see how all of this math is going to eventually turn into something that we've kind of seen before. Okay? But to do that, we're going to need to look at the one equation that we haven't done a whole lot with, which is the radial sort of equation of motion that we derived from Newton's second law, right? So just like before, let's start by drawing that out, or writing that out, where we have m times r double dot minus r theta dot squared equals the negative radial derivative of the potential, central potential, right? Now, this is almost a differential equation that only depends on r. There are a bunch of, v is a function of only r. That's why we have the total derivative right here, not a partial derivative. And it seems like there's only r's in this equation except for this theta dot squared term. And now there's this angular dependence in this equation. What we can do to eliminate this angular dependence is we can say, let's use our knowledge of this conserved quantity little l, the angular momentum per unit mass, and just rewrite theta dot squared in here in terms of L, which is just a constant value. We showed it was constant using this definition right here. Okay. So what we can do is we can take theta dot, or we can isolate theta dot in this equation for L, giving us theta dot equals L over R squared, right? And then if we were to just square it so we can incorporate it into here, we would get L squared over R to the fourth. So let's now just plug this back into the radial differential equation. We're gonna have M times R double dot minus, we have a factor of R here, and then a 1 over R to the fourth factor here. So this is really going to be L squared divided by R cubed in the fraction here. So L squared over R cubed equals negative dV dr, like this. And what we can do now is we can distribute the mass into both of these terms and add this L squared over R cubed factor over to the other side. If we do that, we're going to get M times R double dot equals negative dV dr plus ml squared over r cubed. Okay. So we're already starting to see how this might start to look like Newton's second law. We have m times an acceleration is equal to some function of r on the right-hand side. Okay. What we're going to do now is we're just going to rewrite this one more time as minus dV dr, but rather than writing v, I'm going to write v EFF. The sub EFF stands for v effective. And this quantity right here, v sub EFF, is sometimes known as the effective potential. V is the potential energy of the system. Vf is the effective potential. It's defined, the effective potential is defined as, let's see, the original potential, V of R, by itself, plus ml squared over, see, I want to make sure I do this right, ml squared over 2r squared. Okay. So the idea here is that if you define a new quantity, an effective potential, as a function of r, it's related to the original potential plus this additional term, which we can think of as sort of an energy barrier. This came from just really from this term right here in the radial equation of motion. If we have the potential energy plus this additional term, we can sort of group them together into an overall effective potential. And if we take the negative derivative of this quantity, the negative derivative of V effective, what we're going to see is you're going to end up getting these two terms right here. Take the negative derivative of V of r, you get this. The negative derivative of this is going to give you 2ml squared over 2r cubed, or just ml squared over r cubed, right? And then, let's see, then there's going to be a minus sign too. Oh yeah, because you're differentiating r to the minus 2, right? Well, okay, let's just do this real quick, because ml squared over 2 times r to the minus 2. If you differentiate this with respect to r, you're going to get minus 2 ml squared over r cubed, over 2r cubed, right? The 2's cancel out, giving you minus ml squared over r cubed. Then you have another negative out front, which makes this a plus sign. So the basic idea here is that if you define some quantity V, an effective potential, in terms of the actual potential, the original potential energy of the system, what you have then done is you now have m times r double dot is equal to the negative derivative of an effective potential. What we have done, and this is where I think it's kind of cool, is we have started with, this is the motion of a particle in 3 dimensions, right? This particle is moving in 3 dimensions, but if the particle is under the influence of a central force, we can condense the problem down into a problem of just a single variable. What variable? The radial coordinate, where we have m times just r double dot is equal to a total derivative of something that is effectively the potential energy of the system, related to the actual potential energy plus this additional term right here. Okay, so what we're going to see then in some of the upcoming videos is we're going to say, okay, this equation, and let's just write it out, m double dot equals negative d effective dr. This thing looks just like Newton's second law, where the force is derived from a potential energy. One way in which you can understand the forces acting on a particle given the potential energy, this is why we did the defining forces in terms of potentials in the beginning. One way in which you can understand the motion of a particle is you just plot out the potential energy itself. You plot out this V, whatever your potential energy function is, right? So that's what we're going to be doing in the upcoming video. We're going to say, whatever this V effective is, well, it's this, right? This effective potential energy function, it's a function of r, the radial coordinate, and r only takes on positive values, or 0, so we don't need to extend the graph out into the negative r direction. But we can plot the effective potential as a function of r versus r itself. And then analyzing the shape of the curves for different actual potential energies will give us in turn different curves for the effective potential energy. And we're going to be able to analyze a lot of different systems as long as they're under the influence of an actual central force in some of the upcoming videos, and it's going to be fun. I'm excited. So yeah, hopefully all of that made sense, and yeah, thanks for watching. I'll see you in the next video.